and headed up by people from our northeastern part of the WMI group out of either Bozeman or Glacier National Park. Greg Peterson and Dan Fagery recently published this particular paper where they did reconstructions using dendroecology and then the existing observational record to look at whether there's been a change in snow water equivalent, SWE, over a long period of time. That's the period of time from 1400 to 1950, and a comparatively short period of time, post-1980, to see whether there's been trends in the amount of snowpack across the western mountains. And as you can imagine, red means less snowpack, and darker blues mean more snowpack. And if you use either the observational record or the reconstructed record from tree rings, you can see that over the most recent period and over the longer period of time, there's been an anomalous, there's been less snowpack in the northern Rocky Mountains over time, no matter whether you use observations or dendroecological reconstructions. So what does that mean? We're getting less and less snowpack, specifically if you go from, say, mid-Wyoming up north. It's depending on which of the reconstructions you actually use. The observational records say that down here in Colorado, we're getting a little bit less snow over the past 20 years. The dendroecological reconstructions say, well, we're not getting a whole lot of change in snowpack overall. But this is a good tool for people to start thinking about. And if I was living up in Montana, this would be not only noticeable, but it would be a topic that would suggest that public land managers ought to be thinking about how to manage their lands under less winter snow. We have studies that have been done. This is another very nice portrayal of how snowpack is changing over time, or could be used for how snowpack is changing over time. This is work that was done by Kara Moore, who's a student right here. She finished her work just recently, this past May. She was a student of Stephanie Kampf, and she worked with us on the Western Mountain Initiative. What she took was a very simple, but I think elegant approach toward looking at where snow is most likely to be vulnerable to changing climate. So first she took, it should say here, it will say here. She took avarice data and she plotted where there was seasonal snow. So this is snow that persists until April 1st or later. And so that's what this map is. Here's a map of elevation over here, and also where the seasonal snow cover actually persists. And then she overlaid on that the 2000 to 2010 January, February, March temperatures to say, well, those temperatures that are closest to freezing, one's around 28 to 34 degrees centigrade, Fahrenheit, those are the temperatures that are going to be most vulnerable to warming and with springtime warming. And then she made a series of overlays of these elevations to show which areas are going to have perhaps more vulnerability to global warming, to climate warming, than other areas. And I think it's a really good visual tool that can be used, again, for public land managers. So remember, they're not necessarily trained as scientists. And so visual tools are very effective for suggesting, well, my area might be vulnerable, might be time for us to start thinking about adaptation to climate change. So here's another paper by Greg Peterson, again showing that as Northern Hemisphere warms, so goes western Montana. And that's what these series of lines here are showing. Again, existing data, observed data, going from the year 2000 up to 1900 to about 2000. The red line is the 5-year moving average for western Montana. You can see that it starts, these are anomalies again from the long-term mean being for this entire period of record. You can see that there's been a warming trend in the western Montana 5-year moving average, and it tracks almost identically to the whole northern hemisphere. So we're warming especially up in the northern Rockies, and again, these are the kinds of tools that we use to work with public land managers. These are not necessarily models that say sometime in the future there will be warming. These are existing data that I find very powerful when I talk to public land managers to say things are changing, and they're changing rapidly now. Okay, so that's the climate. The interesting thing is sort of, so what? So what does this mean? And this still falling under detection and attribution. We work very closely with Andrew Fountain at Portland State University. He just published a paper in Bioscience where he talked about what's happening as our small mountain glaciers melt. And here's a picture of mountain glaciers. I'll show you this in a second again. But this is the portal actually to a website. If you're interested, if you go to Portland State University and look at glaciers, he's got all kinds of wonderful before and after pictures, as well as animations of glacier decline over the Pleistocene into the Holocene, into the Anthropocene for all kinds of parts of the western US. So it's very cool. So in the ecological responses in this particular bioscience article that they talked about, again, ecological, not hydrological, they talked about changes to aquatic and terrestrial flora and fauna, and they talked about changes to biogeochemical processes. And I'll pick up again on those biogeochemical processes in a second. But one of the things that Andrew has done, and I think this is just really cool, is he's identified all the glacier locations in the lower 48 states of America. And those are these red dots. The green is Forest Service land. If you can see, there's sort of a beige color. That's Park Service land. But the red dots are where the glaciers exist today. There's some 8,300 of them living on the land surface. And he has gone ahead and looked at how they have actually declined over time since 1900. So some of that is certainly just post-Pleistocene meltback as we've warmed our climate, but the rapidity of change over the past 20 to 30 years is certainly unique in at least our history coming back. So more than 66% of the glacier mass in Glacier National Park is gone, 56 in the Sierra Nevada, about 40% of our glaciers have declined over time. So they're going away. This is going to be a thing of the past. In Glacier, they anticipate by the year 2020, there will be no more permanent snow and ice up there. So what? We come back to melting glaciers. That's still just ice. Those are big lumps of ice on the ground. They're attractive, but what do? Well, they change things. And we have noticed in the work we've been doing up in Lockvale Watershed and now across more of the Rocky Mountains, that there are very strong biogeochemical responses as well as microbial responses to climate change. And the paper that sort of kicked off our hypotheses came out a few years ago. Melanie was a co-author on this paper, Melanie Hartman, Travis Schmidt, who's now with the US Geological Survey. What we found is that in late summer, not snowmelt, in late summer we were seeing large excursions of nitrate, which is a fertilizer, and it was unrelated to atmospheric nitrogen deposition, which is a question we had been exploring for many years. We also see a large increase in weathering products, and we're not alone. This kind of phenomenon's been observed up in Alberta and British Columbia, in Greenland, in other parts of the Rocky Mountains, and now we're exploring where else in the West it actually occurs. So melting ice alters this biogeochemistry. It does that through changes in weathering rates and microbial response. We recognize that it's a transient response. So this is a hydrologic depiction of what happens as glaciers melt. You get some amount of water every late summer as the glaciers melt. Over time, as your glacier, or as glaciers are, if glaciers are persistent and they're not declining over time, you could envision that you'd see a certain amount of discharge each late summer as some of it melts. As the glacier then actually starts to go backwards and never mind. There. Okay, glaciers are melting now, that's where we are. It's going to happen. Once they're gone, we're going to go back to some lower level of hydrologic discharge over time. But what we're studying right now is what happens as these glaciers are declining. And recognize they're exposing sediments, they're increasing weathering rates, they may be exposing all kinds of glacial flower materials that are then leaching out. They are creating new habitats for microbes and other types of vegetation. So we are trying to look at that. That's a very active question for my own research group. We've been looking at ice concentrations as well as stream sediments and stream water chemistry. We've been looking not only in Lockvale, but all over Rocky Mountain National Park and up into the Rawas and soon into Oregon. So this is my field crew from recently. We've got Tim on the lower left. We've got Jared in the middle and Gunnar Johnson. We also have Jared here taking an ice core. This one was from Andrews Glacier, I believe. We have Brooke Osborne, who did this as her master's thesis, asking what happens microbially? Do you increase your nitrifying bacteria if you expose glacier sediments that had been covered over for the past 400 to 500 years? Because these are little ice age glaciers right here. I'm happy to say Brooke will be back. She will be back in October to actually write up the results of her thesis as a paper. So we're all looking forward to that. Here's Ed Hall. He's been working on this project and, of course, driving a lot of the intellect behind it. Ed is at NREL. He's a microbial ecologist, also with the US Geological Survey. And we've also added Claudia Boot to our team, who's looking at the organic carbon changes that occur as glaciers decline. And together, Ed, Claudia, and myself, and Caroline are looking at then what that means for microbial activity and microbial assemblages, and ultimately long-term ecosystem chemistry, biogeochemistry, as it moves downstream. So that's all you're going to get on our research, but there will be great seminars over time coming from Ed, Claudia, and Jared. So let me move on to more detection and attribution, talk about impacts on forests. And I'm going to run you through, maybe race you through, the kinds of studies that my colleagues do. There's a lot of work being done on background tree mortality across the western US, heat and drought-related forest die-off, insect outbreaks, and finally wildfire. So the background tree mortality is done by our colleagues based out of the Sierra Nevada. Phil Van Mantcombe and Nate Stevenson are located here. And they have a unique data set that they've been mining and then applying all over the world. And you can, everywhere that they have these long-term data sets, well, they've used colleagues too. So Tom Veblen, for instance, took the samples in Colorado. These are yearly plots that are revisited to look at tree dynamics, especially tree mortality. And in this particular diagram, the larger the red dot or the blue dot, the greater the mortality that has been observed over the past 30 years that they've been doing these annual tree plots, which I think is an incredible amount of field work. But they've been using this to great effect. So basically what they have found, and these are papers that have been coming out over time, what they have found is an increase in background tree mortality. So this isn't fire, this isn't wildfire. This is just trees that are upping and dying. They're keeling over and dying for possibly unknown reasons, but it looks to me as if it's a drought stress type of response. It looks to them as if it's a drought stress response. They see this regardless of whether they look in forests in the Pacific Northwest, in California, or the interior, which is basically Colorado and Idaho. They see it regardless of the elevation. That's this upper right-hand bar. You see an increase in mortality over time from 1960-ish to 2010 or so. You see it regardless of the DBH of the trees. Little trees, big trees, all of them are susceptible. You see an increase in the background tree mortality rate. You see it regardless of the genus, with the only exception being juniperous. So junipers seem to be exempt from this thing, but firs, pinus, what's tsuga? Hemlock, thank you. Hemlock and also Doug fir, those are all increasing in their mortality rate, and you see it regardless of the age of the trees. So in other words, there's a phenomenon going on, and its background tree mortality is increasing. And another of our colleagues, Craig Allen, has been able to show that this is increasing worldwide. And it's directly related, the more they do the physiological research, to specific drought stress. And I don't know if I have another slide. No, I don't. So one of the things we did recently, a couple of years ago, is we've been working with Nate McDowell at Los Alamos Lab. And we have been coring trees all over the West, including in Loch Vale, my long-term study site, coring trees that are recently dead compared to trees that are adjacent to them that are not yet dead, and using tree ring width, but also carbon isotopes to determine whether there's a difference in their response. And sure enough, the trees that are recently dead show a much different carbon isotopic signature suggestive of drought stress than the trees that are adjacent and still alive. So there's a microhabitat thing going on, but apparently sufficient enough that across the West, this microhabitat drying is probably responsible to killing off these trees. So trees are dying. Trees are dying over the background. Trees are also up and dying in massive amounts, particularly in the southwestern United States. And I'm not going to show you that picture you've all seen before of the pinon juniper forest in the Jemez Mountains where all the pinons are dead, because you've seen it before. But basically, where you have warming temperatures, and I showed that we have warming temperatures, not just during snow, but also during summer events, where you have warming temperatures and you have drought, and we've been through a 10 to 15-year period of drought most recently, you stress these trees to the extent where entire forests at ecotonal boundaries have keeled over and died. And Craig Allen has been leading this charge. Here's a couple of papers, one with Park Williams as the lead and another with Dave Brashears, by showing that this is a phenomenon that's occurring all over the southwestern United States, as well as in many forests around the world in arid environments. Australia, Spain, other parts of the Mediterranean, parts of Africa, parts of South America. So we're seeing extreme die-offs. We're also seeing this background tree mortality increasing. I probably don't need to go into at all the work that's been done on pine bark beetle and insect outbreaks, and I won't go too much into it. This was one of the foundation papers that got us going. Jeff Hickey did this work, Dennis, Jesse Logan, who also used to be here at NREL a long time ago. The story, of course, being warmer temperatures allow these beetles to go through more rapid life cycles. Perhaps forest management practices have allowed more biomass to reach the stage where the beetles can be effective. Drought and warm temperatures prohibit the trees themselves from putting up the defenses. We have tremendous amounts of forest die-off, and you only have to look out the door in order to see that. I'm not sure Jeff actually made this map, but it's very effective. That shows throughout the West the vast acreage that's been affected by beetle kill of some kind or another. The blue is the Ips beetle that affects a lot of southwestern and western types of species. Mountain pine beetle is this red area that's taken over. It's like the tomato that ate British Columbia. And the spruce beetle we see even in Colorado. So vast, vast areas. And Jeff and Craig Allen have been asking kinds of so what questions. Yes, yes, beetle kill is very dramatic and extensive. They've been asking how it affects carbon storage. They've been asking how beetle kill compares to fire in terms of its impact. And the slide that Jeff shows, which is very effective, is that the amount of carbon affected by beetle kill is much greater than that affected by wildfires in the western United States. Still, in spite of the fact that we're seeing increased spatial extent of wildfires, particularly in dry years. And as you can imagine, beetle kill as well as fire contributes to forests in many parts of the West becoming carbon sources to the atmosphere rather than carbon sinks, at least for now. Okay, wildfire, I'm not going to go into a lot of detail because I know far less about what the work that these are doing. But this is work that Jeremy did when he was a PhD student working with us, and with Don McKenzie and Dave Peterson in this particular paper with Tony Westerling. What they found, which may not be a surprise to any of you, is that you have different types of climatic regimes affecting the propensity for wildfire. In the mountains, where you have wildfire, the burned area is negatively correlated with the year of the fire precipitation. Okay, that's a no-brainer. You get less precipitation, you're likely to have more fire. But it's positively correlated with the year of fire temperature. Again, a no-brainer. Warmer temperatures, low precipitation, just like this summer, you're likely to have big fires. The reason for that is that you dry the existing fuels, many of which have been exacerbated by perhaps past forest management practices. That's very different if you go into the southwest grasses and shrublands as well as southwestern forests, where the burned area has been positively correlated with the year preceding, the precipitation for the year preceding. And what that does is it builds up your fuels so that when you do have a dry, warm year, you're able to have these fires persist and expand. So I don't know if that was a novel result. I seem to recall Tom Veblen making that point in a paper some time ago, but it's a particularly nice depiction of that type of spatial phenomenon. So not all fires are alike. And that's a very important message, maybe not for you guys who understand and get it, but for resource managers who for many years, if they weren't subject matter experts, would say, oh, forest management all forests are the same and we need to manage them the same. And this is a powerful tool for saying, no, you don't want to do that. You want to take a much more local and nuanced approach to that. And one way to do that, and I'm going to do my best to explain this paper, and if I fail, I might fail. One way to do that is from a paper that Don just published, where the title tells you that it's highly theoretical. Power laws reveal phase transition in landscape controls of fire regimes. What he did in all of these watersheds throughout the state of Washington, they used dendrochronological data to reconstruct fire history. And from that, then they took topographic data to look at topographic complexity. And what they found is that the propensity for fire, or increased risk of fire, increases according to a power law except where the topographic complexity is such that fires can't spread across a landscape. So they actually take this highly theoretical paper and suggest that you could mimic, if you wanted to manage the spread of wildfire, perhaps you could mimic this kind of topographic complexity on the ground if you knew where on the landscape fires were likely to spread, and that's part of what the power law showed. And then you could maybe manage the spread and extent of fire by applying these types of theory to it. And so this paper just came out. I think it has yet to be applied, but I think it's a very interesting approach toward deciding how you're going to manage on the landscape, because chances are fires will become more intense, more frequent, and more widespread with warming over time. Okay, so that was detection and attribution of climate change, the kind of research that we do. And honestly, I have to say that's where the bulk of our research falls, because it's fun and it's exciting. We then take it to forecasts and scenarios, which is this particular block here. And as I mentioned before, I'm not going to go tremendously into detail with that. I will talk a little bit about some of the modeling that we're doing. We work with Naomi Tague out of Santa Barbara, and a model that she helped develop. Actually, she is now the major developer of this model. It's called RESIS, Regional Hydroecological Simulation System. It's a spatially distributed dynamic model of coupled ecological, meteorological, geological, and hydrological processes. It was initially built off of physiological models that Steve Running helped develop from the University of Montana, and Larry Band, a geographer who spread it across the landscape. So she takes the kind of empirical data that we all provide, watershed level data, and she uses that in order to parameterize these models and ask questions about what if, using various scenarios. Most of the scenarios are sensitivity analyses. We'll take a model, we'll apply it to an area, we'll run it for the years of record that we actually have, and then we'll do what happens if we raise the temperature +2 degrees, +4 degrees? What happens if we raise the springtime temperature? So we do those kinds of types of scenarios over time. One of the places that she's been applying this, and it's really very exciting because it seems to be working, is this area in the southwestern United States in New Mexico, where they've been looking at the physiological responses to mortality. I mentioned Nate McDowell before. So again, this is work that Nate's been doing with Craig Allen. And these are extant data. They come from dendrometers on a bunch of ponderosa pine data. And what they find is, depending on the elevation, which is a surrogate for water stress, you see changes in tree, whatever dendrometers do. Trees expand with water and they contract when they're drier. I'm a biogeochemist, I'm sorry. These are data, and at low elevations, over the months, you can see increasing amounts of difference. This is cumulative basal area increment difference between wet and dry. So over the months, as it gets drier during the summertime, you can see a greater change in the ponderosa pines at the lowest elevations than those at the highest elevations, which really don't change at all because they're not water stressed. They get enough moisture, probably from orographic precipitation and cooler temperatures over time. So they took this and they mapped it on the landscape, and that's what this is up here on this top right portion. This is actually Little Frijoles watershed, doesn't matter. It's in Bandelier National Monument. Low elevation is on the bottom of this map. High elevation is on the top and in the green. The yellow is pinyon juniper woodland. The ponderosa pine forest is green, and the areas are red are the areas where ponderosa pine did persist and have recently died off. So they have tree ring records for all of these trees. And they applied this physiological idea that carbon starvation due to water stress is what's killing these trees off. And then they modeled it using a series of scenarios. So the baseline map for the Frijoles Basin, that's what that is. You'll have to squint, but that's actually the same basin. The baseline shows that there's an area of higher risk toward carbon starvation and tree mortality in the lower elevations. That's not a surprise. And that it expands under these scenarios of +2 and +4, and you actually can recreate the tree mortality that occurred. So what it means is that the model is actually giving us results that make a lot of sense. Models are tools that can be used to generate hypotheses. They can also be used as powerful tools to show managers what might happen under different types of scenarios. And that's how we're applying them today. Some of the other scenarios and forecasting we're doing is looking across the West and looking at the combined disturbances that may occur with fire and insect outbreaks and increasing temperatures and increasing water stress. This is something that recently came out with that Jeff Hickey did, and these are actually slightly declining carbon stocks over time for several different types of species, suggesting that with combined disturbances, we're likely to see less carbon on the landscape. That also translates to less, probably, forests on the landscape. There's a number of assumptions here, none of which I probably know very well to describe, as to whether you would see forests regrow over time. But again, this is a good management tool to suggest that, especially for resource managers of public lands, you can't think about one threat at a time. And very often when we talk, especially to Forest Service managers, we say, let's talk about climate change. And they go, I can't, I'm dealing with beetle kill. And you try to say, that's the same thing. But they don't get it. Or over time, they're beginning to get it. But then when you say beetle kill and fire and water stress and perhaps changes to your hydrology, we're trying to do that in a way that doesn't frighten them off and instead gets them to start thinking larger, multi-scale. So I'm gonna end with how we're doing that. That's this hands-on leadership in adaptation and mitigation planning. And so that's this bar over here. And this is actually very interesting, and this is work that has been continuing for about 7 or 8 years, and we're ramping up again with the Climate Science Centers and with Dennis and Jeff. So we've held a number of workshops over time, and these, what's that? And these workshops have happened all over the West. I could say we've all run these, those of us who were part of the Western Mountain Initiative, and then we're revisiting many of these areas and coming back, because part of the way to build long-term science manager partnerships and to really implement change is to not do one-off types of activities. We go in, we work with them, again, cross-boundary. We call these bridging boundaries because it's not just Park Service, it's Forest Service, it's tribes, it's counties, it's cities. We bring them all together to talk as a group about what can happen regionally and how can we best manage them together. So the Forest Service just published this thing. We all had a big hand in it. It's a guidebook. I'm sure people are using the guidebook, but what really helps is you go physically plant yourself in their region and you talk to them all the time and you work with them over and over. And that's because this is the way they view climate change. You know, it makes it very hard, and it's very paralyzing for many resource managers to say, I'm going to deal with climate change right now. It's either damned if you do or damned if you're not. So what we've been doing is going in with a philosophy for adaptation that says that the onset and continuance of climate change, in addition to all the other stresses they already deal with today, the invasive species, the air and water pollution, the habitat fragmentation, they all deal with those on a regular basis. In addition, the onset and continuance of climate change means you got to think differently about how you manage these lands than you have in the past. And so it becomes a social science issue as well as a scientific one. Preparing for and adapting to climate change is as much a cultural and intellectual challenge as it is a scientific one. We can all talk till we're blue in the face about the trends that we're seeing and what it means, but until they believe it, until they actually say, okay, now I'm ready to do something, then it's not going to be enough. So this is a large part of our measurement, our arguments as well. Uncertainty does not equal ignorance. We know a lot. So we work with resource managers to address climate change effects as risk, to address adaptation specifically as risk management. And then we talk about a framework for adapting, and this is where we are. And we're actually starting up a very cool program again in Rocky Mountain, in northern Colorado, in Rocky Mountain National Park, to establish a long-lasting science management partnership to work on building trust in community, not just with the scientists and the managers, but among the managers themselves. Parks and Wildlife in Colorado, along with the Forest Service, along with the Park Service, along with the mayor of Estes Park. All of these people need to work together if we're going to develop a regional program that works. We want to identify scenarios for future conditions. I personally like to do this with a napkin in the back of the envelope. You know things are going to get warmer and drier. What would happen if? So there's a lot of ways you can do that. We evaluate vulnerability and risk. The Park Service themselves have been very proactive in doing that. I think the Forest Service lags some, but they're coming along. And then talk about win-win types of solutions. If you reduce your atmospheric nitrogen deposition, you reduce the vulnerability of your alpine flora to drought, for instance. There's a win-win type of solution. And then, of course, monitoring is extremely important to all of this. And many agencies say, yeah, it's important, but we can't afford it. So a large part of our argument is you can't afford not to do it. Hello?
Oh, you are. Okay. Yeah, you want to keep it in the office?
So I have, that's basically the end of my talk. Not just thanks to the guy on the phone. The kinds of things that we do with these long-term place-based research, extrapolation of processes across the West. I haven't shown you a lot of those. We have some. Well, I did show you some of the climatological extrapolations and these close relations with resource managers. And that's basically what our Western Mountain Initiative is. You just got the high elevation overview. So thank you.
Thank you, Joe. I mean, this is exactly what we were anticipating, trying to get the sort of integrated view of some of the research going on in our region. And so I'm sure there's questions.
All right,
Jill, this is half the story. I'm sure you know about the other half of the story. Is it shrubs that come in? Is it grass that comes in? And I can't say, are they looking to see if the soils is changing? You know, as the trees disappear, they're not disappearing. What's going into the landscape, and who's studying that?
And, well, I think Craig is doing some of that work, and especially he's doing a lot of it in his own long-term research site in the Jemez Mountains, which burned down to bedrock just last summer. So he had long-term plots there where he had maps, very interesting maps, from Native American habitation since, I don't know, post-Pleistocene, coming in, European settlement, and he could actually map the rise and fall of different tree species and well, mostly tree species, and shrub species over time. So he has that kind of history going back in time, and then what he hopes to do with the long-term research that we're still doing and monitoring is see what happens, what comes back. So in the 1950s, there was a very large drought, for instance, in the Jemez, and ponderosa pine had extended much lower in elevation before the 1950s drought, and then it retreated to where I showed you on those maps. And what came in instead was pinon juniper. Those pinon juniper are now, well, at least the pinyons are gone. I think the junipers no. The pinyons were gone because of the drought in 2002. And then the junipers went in last year's fire. So what comes in now, that's what he's looking at. So there are those kinds of place-based studies, again, due to long-term monitoring, that we hope can answer some of those questions. We have a very interesting phenomenon just in Loch Vale right now, where our old-growth Engelmann spruce is dying. So we're seeing 400 to 700-year-old trees, tremendous amounts of blowdown in all over that belt of forest in the Front Range of Rocky Mountain National Park. We'll be able to monitor what happens over time, I hope. David.
I'm here with our intern, Phenomenon, who is working on the Gloria initiative, the
Oh,
Global
Gloria.
Observation Research Initiative.
You might want to speak louder, or I'll repeat.
Okay. Yeah, so we were wondering what the connection of the Western Mountain Initiative is to the Gloria project.
It's tangential, I should say. There are Gloria sites in, so Gloria is an alpine vegetation monitoring program set up for mountain research areas around the world. And it was based out of Austria. The idea was to put up sentinel vegetation plots on the cardinal directions of mountains and monitor them over 5-year, 10-year time, 5-year. Every 5 years, go back and look at what's happening. Are species creeping uphill? Are species changing in biomass? Are you seeing new species, loss of others? So there's a Gloria site, or several, in Glacier National Park. We established one in Rocky Mountain National Park. I had nothing to do with that. I believe there's some in the San Juans. Yeah, yep, Crescent Butte. So is that part of WMI? No. Do we intersect? Yes. And we'll be maintaining those, well, someone will be. Someone will continue to go up and monitor those plots. But that's another question, Elder just left, but that's another answer to long-term monitoring of vegetation dynamics.
Could you hold it down out there?
Just cut them off.
We could do that. We're done.
I cut them off, still some people on.
They lose.
I
Yes.
had kind of a people-related question on those adaptation kind of cross-boundary workshops that are happening. Maybe what facilitation of those looks like, if it's by USGS or another federal partner or a private organization, and if they're entirely discussion-based or if there are products that come out of those discussions.
Yeah, no, really good questions. The ones that I've been directly involved in, and there are 3 of those, we did not have we didn't hire a facilitator. So the Crown of the Continent, which was basically northern Montana going up into British Columbia and Alberta, and then the one that we recently held in the Black Hills of South Dakota with Badlands and Custer, a number of organizations, we had tremendous help. Oh, and the one we held in Rocky Mountain National Park for northern Colorado. We had tremendous help from Jess Thompson, who recently left Colorado State. We're all very sad. But Jess is an environmental communicator who received funds with us to start holding these workshops. So she had brought in a number of her student interns, as well as her own prodigious skills, to make sure that these groups were collegial, that we were moving toward, first, a shared understanding of what climate activities are in their region and what resources might be vulnerable. And that was very much a group discussion. We weren't going to go in and say, your prairie dogs are at risk. That was something that came out of their discussions. And in the Black Hills and in western South Dakota, what came out as most at risk were ranching and agricultural activities, not natural resource types of questions. So where it becomes important to maintain that continuity is that they come out of these working groups, workshops, with lists of important topics that they themselves choose to pursue. Do they pursue? That's why we're back again in Rocky Mountain National Park, because they all go out, they're all charged up, these are very successful and very energetic types of activities, and then nothing happens. So what we have discovered from the workshops that were held up in the Pacific Northwest with Olympic National Park and National Forest is that it takes a person, in this case it was a postdoc, to be the glue, to say, okay, remember you had those objectives, let's work on them together. And so she was the cheerleader, forget her name. She was the person who kept the activity going, kept them coming back to the table to say, okay, let's develop plans. And they actually did. That's a wonderful example of how they addressed specific climate change impacts that they, across jurisdictions, were going to address. So we're trying to do that now, reviving with Amber Childress, who's a student of Dennis's, and Dennis, and Rocky Mountain National Park and the National Forests. We're trying to do that now with northern Colorado.
Great, thanks.
Yep.
What you've shared with us today is tremendously valuable for guiding how we're going to deal with climate change and adaptation management and so forth. And I'm wondering how the Western Mountain Initiative, well, it seems like this is a message that the LCCs can really use as part of their guiding principles. And I'm wondering what connections exist now or how we can help form more of those connections.
So David's question was how can this type of approach be used in conjunction with these landscape conservation cooperatives that the Department of Interior has set up? And I'll throw it back to you. I have very little contact with the LCCs, to the point of maybe saying zero. So it's an opportunity for sure, if you think it could really be helpful.
Yeah, I mean, the steering committees and the stakeholders of the LCCs could really benefit from learning more about what's going on here.
My understanding of LCCs is that they were very organismal. You know, you didn't see pictures of fish here or elk or bears. we would love to have partners who help do that kind of work, but we meet them halfway. Tracy?
I'm
Stacey?
curious whether you saw the papers and publications and things that you've produced over time, whether there's anything more synthetic that you've published showing a more long-term view of your approach and the implications and impacts and collaborations and all of that.
What-
That's very interesting.
There is a book in progress. I say that with half a smile because it's been in progress for about 10 years. The idea to develop a not-for-scientists definition of climate change. And I think there's a working title which is Mountains in the Greenhouse. Ugly, but there is that kind of synthesis. Every year we hold a meeting, and we meet once a month actually as a group on the phone. And we always discuss this idea of how can we be, what emergent properties come out of what we're studying. And I think they are, but so far it's related, well, the forest types of dynamics that I've presented, they can easily be synthesized up. I don't think they have been yet. The kinds of glacier melt study, we're way far behind that. But we hope to be able to say something about biogeochemistry and productivity in aquatic ecosystems related to glacier melt. What we have done that's been very interesting is we've been requested and have produced synthesis papers on our process. And I've been over to Europe several times to speak to European mountain research groups about how we all collaborate and why that works. And for some reason, that's a topic of amazement to them because they're very much more disciplinary oriented. So the idea of interdisciplinary congenial collaboration is something that we've become more known for actually than our results. So I don't want to dismiss that. I think that's a very important topic that we all, I think at NREL and certainly Colorado State, take for granted. But it's not the norm in much of the world that scientists collaborate and share.
On that note, I think we should thank Jill for sharing her perspectives and her approaches, and she'll be around for